Hey folks, today we're going to talk about finding an error bound for a series, specifically an alternating series. We'll have two techniques for error bound. The error bound for alternating series only works for alternating series. So I'm going to take us back here to building that polynomial in the first video for chapter 9. We had a sine x, and what we did was we said, hey, let's, this graph of y equals x looks a lot like sine x. Okay, not a lot, but if you stay really close to 0 where we were centered, they looked a lot alike. And then we did something kind of weird. We graphed the error, and we looked at the error and we guessed the equation, thinking, hey, if we have an estimate and we add our error back on, we'll get a better estimate. And that's exactly what happened. We ended up guessing that error to be a negative x to the third over 3 factorial from our calculator. And it's kind of interesting that when you use this graph to approximate sine, the next term represents that error. And then we graph this, and then we graph the error, and I made a really miraculous guess at what that error actually was. I think I came up with x to the fifth over 5 factorial. And we said, well, if that's our error, let's add it back onto our approximation and get an even better approximation. And I want to point out again, when we use this as an approximation for sine, the very next term represents the error from using those first two terms. And then I guess we can probably make a little guess here. If I were to use these first three terms to approximate a value of sine, what would our error be? And we should be thinking, well, wow, the error is always represented by the very next term, the one we didn't use. That's why we kept adding it back on, right? Okay, and that's the basic gist for this error bound, is the understanding that that first term you didn't use in your approximation, we use those first three terms to approximate, the next term represents the error from using the first three terms to approximate. Okay, so first of all, let's take a look at what this alternating series bound error is. There's a little formula for it. It's really what we just came up with. Alternating series error bounds, your error is going to be less than or equal to the first term in the sequence not used. So if you can just find the next term, you're in good shape. Now, this only works if the series does alternate, and that means it's a positive term, a negative term, a positive term, a negative term. Or I guess it could have started negative, positive, but it's not just, hey, two negatives, two positives, that's not alternating. It has to be 1 and 1 and 1 and 1. And then the terms decrease in absolute value to 0. All that means is if you ignore the signs, whether it was a positive term or a negative term, the numbers get smaller and approach 0. Okay, let's see. So let's try one. Let's find the error bound. If a fourth degree Maclaurin polynomial, think to yourself where that's centered, is used to approximate the value of cosine of 0.5. Okay, so first thing we need, we're going to use a fourth power Maclaurin polynomial for cosine. So we have to find it. Hopefully we've got it memorized and we're not going to have to take these derivatives for cosine. We should have sine, cosine, several of these already memorized. So let's go ahead, and I know the first term is 1 because it's always the function value at center. Maclaurin means we're centered at 0. Cosine at 0 is 1. Easy to get the first term. And I remember this one alternates also, and it's all the even powers and factorials. Oops, I'll stop right there because that's a fourth degree Maclaurin polynomial that represents cosine. Now, if we wanted to actually do the approximation, nowhere in what's written here does it say I actually have to do it, which is good because I think it's just a pain. But if we were to approximate cosine of 0.5, we would just plug a 0.5 in for all these x's, get out our calculator, do a bunch of annoying button presses, and we could come up with an approximation, right? But it really doesn't want to know what the approximation is. It just wants to know what the error would be if we decided to use the fourth degree. Okay, so let's check it out. Does this alternate? Yes, it does. Positive, negative, positive, right? And do the terms get smaller? 1 over 2 factorial, 1 over 4 factorial. These do. Yes, they do. So we have met both criteria for this alternating series. And so all we need to do is find the next term. If it meets those criteria, then the error is the first term not used in our approximation. I really should say it is less than or equal to. So here we go. Our error would be less than or equal to, and what is that? That would be the one with the 6 over 6 factorial. It doesn't matter that it's negative because we're taking the absolute value of that. And so in reality, for an approximation cosine of 0.5, where we plug all the 0.5s in, our error would be less than or equal to, I'm going to leave, I'll put the negative in just so no one gets upset with me. We'll plug in a 0.5, and that should be the error. And you can go ahead and put that in your calculator if you want to. I get that the error is, approximately 2.170 times, 10 to the negative fifth. That's pretty good, right? We're not off by a whole lot. On the AP exam, you're free to just leave it in this format. All right, folks, that's your introduction to the alternating series error bound.